In my previous video, Understanding Understanding, I went over my theory of understanding and a possible method for quantifying it. After critically examining the previous understanding formula, I recognized that it contained a major flaw. The number of conditional statements is not an effective way of quantifying the versatility of a theory, as conditional statements can be worded in such a way to produce errors. In this video, I will try to rectify these mistakes by presenting a new method of quantifying understanding. Let me begin by introducing a specific question. Which theory is more versatile, the proper method of multiplication or the 11 multiplication trick? The answer is seemingly obvious, the first one, but we must be careful in how we define and measure versatility. If we measure versatility by the amount of situations which a theory applies to, the surprising conclusion is that both multiplication techniques have the same versatility. This can be easily proven. First, let us write down all the possible situations that each theory applies to. For simplicity, I will only deal with whole numbers. In each cell, the multiplier is equal to the row, while the multiplicand is equal to the column. All of the cells are applicable to the proper method of multiplication, but only those highlighted yellow apply to the 11 multiplication trick. If we start from the upper left corner, we can list every single problem in a straight line. We can do the same for the highlighted cells using only a slightly different pattern. By placing the cells into brackets and lining the two sets next to one another, it is apparent that they are both of the same size. Therefore, if versatility is defined by the amount of situations which a theory applies to, both theories have the same versatility. So what we need to change here is our definition of versatility. Let us instead propose this. The versatility of a theory is measured by the amount of situations which a theory applies to out of a certain set of situations. From this table, or a certain set of situations, it is apparent that the proper method of multiplication would have a versatility of 100% because it applies to all of the situations. But what would the versatility of the 11 multiplication trick be? Because there are 23 yellow cells out of the 144 cells, the versatility could be about 16%. However, we will only know the true versatility of the 11 multiplication trick if we zoom out enough. Having done that, we now see that the versatility of the trick actually becomes smaller and smaller the more we zoom out. Written mathematically, we can show that the true versatility of the 11 multiplication trick is 0%, which is a result completely opposite to that of our previous definition for versatility. This method of measuring versatility is wonderful, as it allows us to avoid counting conditional statements and bypasses the fact that sets within sets can be the same length as one another. However, this method is weak in how it defines applies. What if a theory produces an answer that is very close to the correct answer, like the non-relativistic velocity formula? Should its versatility be equivalent to a theory that produces highly incorrect answers? Obviously not, so we must adjust our definition accordingly. Let us borrow the machine learning concept of cost to tackle our problem. The x-axis represents all possible inputs, and the y-axis represents all possible outputs. The height of the blue dots represent the correct outputs for a certain input, while the red line represents the outputs of a certain theory for certain inputs. The length of the black lines represent how inaccurate the theory is, and the average length of the black lines is the cost. The cost can be written mathematically as this concise formula. Here, the expression within the absolute value sign calculates how incorrect a theory is at certain points, while the summation sign finds the average of these values. Because cost is inversely proportional to versatility, just like the number of conditional statements, it can take its place in our original formula. Let us now apply it to our previous problem. For example, let's say a robot only knows how to use the 11 multiplication trick and was given the problem 27 times 32. Applying the 11 trick would result in the answer 352, while the correct answer is 864. Plugging these values into the accuracy formula, we see that the robot's response had an accuracy of about 0.41. So now we need to solve for the cost of the 11 multiplication trick. To solve the cost for this specific case, the cost formula is not necessary. As we zoom out further and further, the cost grows larger and larger because more cells end up farther away from the yellow cells. This causes the cost of the 11 multiplication trick to be equal to infinity. Solving the understanding equation, we see that the robot's understanding of the question, what is 27 times 32, is 0 units of understanding. Hopefully, I have removed the difficulties that the previous understanding formula brought about. If any new problems arose due to this video, please leave a comment below on what you found. Thank you all for watching.